Good day, I'm Maile Madziba. Welcome back to our channel. We continue with our class test 1 of 2011 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. So we are looking at part 6, which is the last part of class test 1. So this is actually the problem statement. It says a raw material containing 80% Na2CO3 plus 10 it says a raw material containing 80% Na2CO3, 10 H2O, and 20% inert solids, which are insoluble. And the raw material is dissolved in fresh water to give a saturated solution at 17 degrees Celsius. This solution is passed through a filter to remove the inert solid as a wet filter cake. The clear liquid from the filter is treated with phosphoric acid, which is H3PO4, to produce disodium hydrogen phosphate, according to the chemical reaction equation, which is very balanced in itself. It says now that again that the phosphoric acid is charged to the reactor as a 40% solution of H3PO4, this is it, in water, and also the charge is stoichiometrically correct. And also it says that the CO2 is removed from the reactor as a gas, and the reaction goes to completion. The product stream contains only dissolved Na2HPO4 and water. So they are basically saying that this product stream contains only Na2HPO4 and water. This is because the CO2 here has been removed as a gas. So now we have answered the first question of the class test, and this is now the second question. And on the second question, we had A, B, and C. We answered A and B. Now we left with C. And this is what C says. It says calculate the percentage of, let me just write calculate up here. Calculate the percentage Na2HCO3 in the product stream. They want to know the percentage of the NH2HPO4 in this stream. Remember, there's NH2HPO4 and water. They want to know how much of the Na2HPO4 is in this product stream. So I've outlined a couple of steps, only 3 steps. So I'll start with the very first step, which I named step 1. So in our step 1, we're going to calculate the total water in the product stream. There's a couple of streams that are bringing water here. The first one you can see is the Na2HCO3 with water. There's water coming in. Also the H3PO4 charge, it also comes with 60% water. And also you can see from the chemical reaction, there's also water formed. So the first step is to calculate all the water into this product stream. So let me just outline it and write it down here that calculate the total amount of water in the product calculate the total amount of water in the product stream. So that is actually our step 1, and for us to do that, we're going to start with the water in the Na2CO3 solution, the saturated solution. So I can just write therefore water in the Na2CO3 saturated solution is equals to, let's remember that in our previous, we have all the information, much of the information to this question. In our previous equation, we're told that we need to use 100 kilograms per hour of the Na2CO3 and water. That is actually what we've been given, that we need to use that as a basis. And also, we have calculated already that the Na2CO3 into this stream is actually 15.825. So that is actually what we calculated on 2b. We already know that we are given a basis of 100 kilograms per hour of the whole solution here, and also we did a calculation and we find that in this 100 kilograms per, in this 100 kilograms per hour of solution, there's actually 15.825 kilograms per hour of Na2CO3. Then we can just make the balance, and we know that the remainder in the 100 kilograms per hour is actually water. And with that said, we'll just say the water in the Na2CO3 saturated solution is equal to 100 kilograms per hour minus 15.825 kilograms per hour. If it's not so clear, go start, or maybe you have not started with question B of the same question. Go there. I also advise that you start with question A. That will make things much more easier. So now we know now the amount of water coming through the stream of the Na2CO3 solution. Now the second one is the water. Okay, let me just show it here. Now we're going to figure out the water in this stream here. So water in the H3PO4 solution is equals to, remember that we already are told from this problem statement that the solution contains 60% water and 40% H3PO4. And also in our previous questions, we actually have calculated the total amount of flow rate of the stream here, and we calculated that total amount to be, it was 36.6 kilograms per hour. Already we calculated in B that the flow rate of the stream, the H3PO4 in water, is actually 36.6 kilograms per hour total. So if we have that total and we know that 36.6 kilograms per hour, 60% of it is water. So it's not so, it's actually straightforward to calculate the amount of water there, and we'll do that. So the water in the H3PO4 solution is equals to 36.6 kilograms per hour multiplied by 0.6, and that gives you 21.96 kilograms per hour. So now we have figured out the amount of water here and also the amount of water here. So the amount that's left is the water that actually gets to be formed from the chemical reaction, as you can see it here and there. And for us to actually calculate the amount of water that has been formed, we need to go back to the chemical reaction. We know for sure that we know how much of Na2CO3 has reacted, because we are told that the reaction goes to completion, and we are also told that the charge of the H3PO4 is stoichiometrically correct, but we sorted out that in A and B, so it's not a problem. So now what we're focusing on is that we know that the amount, if all of the Na2CO3 if all of the Na2CO3 has reacted with H3PO4, then that means the number of moles of Na2CO3 that have reacted is equal to the same amount of the water that has been formed. This is because from the chemical reaction it's actually 1 mole and 1 mole. So let me just write that down. Let me just say the ratio of Na2CO3 and H2O formed from the chemical reaction. The ratio of Na2CO3 and H2O formed from the chemical reaction equation the ratio is 1:1. And now if the ratio of Na2CO3 is 1 and H2O is 1:1, then the number of moles of Na2CO3 is actually the number of moles of H2O, and that is exactly what we're going to be doing. Now I just want to write that down here, that the number of moles of Na2CO3 reacted, let me just write that the number of moles of Na2CO3 reacted is equals to the number of moles of H2O that has been formed, right? And that is equals to, from the previous equation, we have already calculated the number of moles of Na2CO3 that has reacted, and we found that to be 0.14929 kilomole per hour. So that is actually the number of moles. So we know, for sure, we know the mass of the water here and also the mass of the water here, the flow rate. Here we know that we've already found out the number of moles of the water. And if we have the number of moles of the water, we can actually use the molar mass of water to calculate the mass flow rate of the water. And we'll do just that. So we can just say the mass flow rate of H2O is equals to it's 0.14929 kilomole per hour multiplied by 18 kilograms per kilomole. We know that the molar mass of H2O is actually 18 kilograms per kilomole. So now if you use your calculator, that gives you 2.68722 kilograms per hour. So that becomes the mass of the water from the chemical reaction. So now the total amount of water in the product stream is equals to, the first one we calculated to be here if you can check, I forgot to put the final answer. So it's 100 kilograms per hour minus 15.825 kilograms per hour, and that gives you 84.175 kilograms per hour. So the water here is 84.175 kilograms per hour, and the water here we calculated to be 21.96 kilograms per hour, and the water here we calculated to be 2.6722 kilograms per hour. So the total amount of water in the product stream is equals to 84.175 kilograms per hour plus 21, let me write it here, plus 21.96 kilograms per hour plus 2.689 kilograms per hour. Now if you do your total calculation, you'll find that gives you 108.822 kilograms per hour. So now we know that the total amount of water in the product stream is actually 108.22 kilograms per hour. Now, after we have figured that out, we then going to need to find out how much of Na2HCO3 that is in the product stream. Because remember, the question says they want the percentage of Na2HPO4, which means we need to get the total amount of the whole product stream. But now, at least we've made progress because we figured out all the water. Now we need the Na2HPO4. So this takes us to our step 2. Now in our step 2, we are calculating the amount of Na2HCO3 in the product stream, right? So now our step 2, we're calculating we need to find out how much Na2HPO4 is actually in the product stream, and we're going to use the chemical reaction equation. We know that the Na2CO3, we know the number of moles of the Na2CO3, and we also have the balanced chemical reaction. So we know that the ratio of Na2CO3 is equals to 1:1 with Na2HPO4. So that means that the number of moles of Na2CO3 is equals to the number of moles of Na2HPO4 is equals to, here we have it, 0.14929 kilomole per hour. So now we know that the amount of Na2HPO4 in moles is actually 0.14929 kilomoles per hour. So with that said, we can just use the molar mass of Na2HPO4 to get the mass therein. So the mass of Na2HPO4 formed is equals to the number of moles Na2HPO4 multiplied by the molar mass Na2HPO4, and that equals to the number of moles is 0.14929 kilomole per hour multiplied by the molar mass of Na2HPO4. If you use the periodic table, is 142 kilograms per kilomole. Now the total, then if you use your calculator, it gives you 21.2 kilograms per hour. So now that tells us that Na2HPO4 in the product stream is actually 21.2 kilograms per hour. So now it takes us to our, okay, let me just write the total here. Let me just say, therefore, total product stream is equals to the total water, which is 108.822 kilograms per hour, plus the Na2HPO4, which is 21.2 kilograms per hour. And if you use your calculator, it gives you oh no, I don't know what is it. I didn't use a calculator. I left it like this. There's no problem. All right, so we'll see that. Let's go to our step 3. Our step 3, then in our step 3, we then answer the question. You see, let me see if I don't have a clean sheet. Well, I can just use, okay, let me just use a cleaner sheet here. So step 3, calculate the percentage. We're now answering the question. Calculate the percentage of Na2HPO4 in the product stream. In the product stream. So therefore, you can just say the percentage Na2HCO3 in the product stream is equals to mass flow rate of Na2HPO4 all over total mass flow rate and multiply by 100%. I didn't have a space to have that 100%. I hope it's visible that it comes here, but mathematically it should be easier for one to tell. So yeah, and with that said, so therefore the percentage Na2CO3 is equals to the mass flow rate of Na2CO3. We calculated it to be 21.2 kilograms per hour. So it becomes 21.2 kilograms per hour all over the total mass flow rate, which I didn't actually use a calculator to add it up, but I used the calculator at the end, so I'll just write it as it is 108.822 kilograms per hour plus 21.2 kilograms per hour multiplied by 100%. Now if you get to use your calculator here, you'll find that percentage Na2HCO3, percentage Na2HCO3 is equals to 16.3%. So that becomes our final answer. The percentage of the Na2HCO3 in the product stream is actually 16.3%. So thank you for your time. This wraps up our class test 1 of 2011. This was a very interesting class test because this is actually the class test I wrote 11 years ago in 2011. So I hope to meet you again in our next video. And if anybody can, please find my email in my YouTube channel and email me the study guide either in pictures or PDF so I can keep uploading. However, if I won't be able to find the study guide, I have another class test too that with time I will then do it in parts and also upload it. Thank you for your time and let's meet again in our next video.